Alright, now that we know how to parameterize surfaces, what if the surface that we've now parameterized, what if we want to find the tangent plane, and what if we want to find the surface area of something which is now parameterized? So you might recall that our formula that we used to use to find the tangent plane was z minus z naught equals partial of x times x minus x naught plus the partial of y times y minus y naught. And if we wanted to find the surface area was defined to be the double integral over d of the square root of 1 plus the partial of x squared, that's an x, plus the partial of y squared dA. And both of those were perfectly fine if z was a function of x and y. So this is only good if z is some kind of a function of x and y. But again, the question is, what if now our surface is parameterized? How can we still find these things? So that's what we're going to talk about here. So if we have some kind of a surface, try and keep it relatively simple here. Some kind of a surface, just some kind of a thing floating up in space here, whatever this thing does. If we have some kind of a surface and we want to parameterize it, if we want to find the tangent plane, well, in order to find a tangent plane, we really need two things. We need a normal vector and we need a point. Well, let's go ahead and put a point on here. So maybe we'll have our point. Point maybe right there. And we're going to call that point, just whatever the point is, our x naught, y naught, z naught. What we still need is a normal vector to this. Well, what if our vector is defined as some kind of a vector where x is dependent upon some u and v, y is dependent upon some u and v, and z is dependent upon some u and v. And those could be any generic values. They could be x and y, they could be theta and phi, they could be rho and theta. It's really just going to depend on how we've parameterized them. So now our surface here is going to be defined parametrically somehow, where u and v are going to really become the independent variables. Well, what we would need to do is we would need to find the partial of r with respect to u. So we'd have to find the partial of r with respect to u, and we would have to find the partial of r with respect to v. Partial of r with respect to u, let's just say that u, for instance, in this case is x. The partial of r with respect to u would be a vector maybe which goes in that direction. And then the partial of r with respect to v might be a vector which moves in that direction. And these two things right here do not have to be perpendicular. As a matter of fact, it's quite likely that they won't be perpendicular. But what they are is that both these vectors lie in the tangent plane. Okay, both of those vectors are going to be coplanar, and they're going to hit this plane at that one specific point. So in order for us to be able to find a normal vector, what we're going to do is we're going to take and we're going to cross r of u and r sub v. So we're going to take and we're going to cross r sub u and r sub v, because what that'll do is that will give us a normal vector to both of these vectors, and that will be something which is perpendicular to the plane. So that will become our normal vector. And we already have our point. Okay, our point is defined above to be x naught, y naught, z naught. And our normal vector, when you cross these two, we actually are going to get some kind of a vector out of it. And remember that we typically are going to call that A, B, C. So whatever you get from actually crossing these two things, when you plug two vectors in there, you're going to get A, B, and C out of that. So the tangent plane that we would get is going to be A, x minus x naught, plus B, y minus y naught, plus C, z minus z naught, equals 0. And that'll be our tangent plane to this surface. Alright, so now we've defined a tangent plane to the surface. Well, why would I want to do that? Why is it even necessary to define a tangent plane to this surface? Well, what if we were to take and we were to cut this entire surface into very, very small patches? So maybe we'll have let's try this in yellow and see how it looks. Got your lines like this. And then we're going to have our lines like this. So we're basically cutting this thing in the direction of x and y. And if we can make these little patches extremely small, now we're going to say that this patch right here is a very, very small patch. If we can make that patch extremely small surrounding that dot, then basically what we're going to have is we're going to have a whole bunch of little parallelograms. So let's go ahead and write that down. If we cut the surface into small enough patches, each one will be a parallelogram. Is it ogram or agram? I don't remember. Close enough. Parallelogram. So what you would have from each one of these things is basically you would have your two vectors. Again, these do not have to be perpendicular to each other. If they were perpendicular to each other, they would create a whole bunch of rectangles, and it would be pretty simple to deal with there. But since these are not necessarily perpendicular, remember the idea here is that we can find the area of the parallelogram, because the bottom vector here could be the same as this vector right there, and then the side vector on the left could be the same as this vector right there, and it would create a parallelogram. And remember how you find the area of a parallelogram is the magnitude of A cross B. Well, we've already done a cross product of the two vectors. We've taken the two partial derivatives of each one of those vectors. So we found, the direction and how they react as they go in the specific direction. So we found that already. So what we have from up above here is we're going to have that the magnitude of RU cross RV is going to be the area of one patch. So if I can find the area of this one specific patch right here, if I want to find the area of all of them and then add them all up, well, now we're talking about a double integral. So we're going to take and we're going to do a double integral over top of our domain of the magnitude of RU cross RV dA. And what that's doing is assuming that U and V in this case represent X and Y. Again, it doesn't matter. It could be whatever variables we need it to be, but you're going to take this patch and this patch and this patch and this patch, add them all up in in the Y direction or in the X direction first, but I'm going in the Y direction. You're going to take all these patches here and add them up in all the y directions, and then once you have the sum of whatever these things are out here, we'll write, these would be the sums, then you add them all up in the x direction. So you would double integrate over the domain, and you would get the surface area. So let's go ahead and see that this actually works. We're going to actually use an example just in general. So let's say that we parameterized our surface. Let's go red. Let's say we parameterized our surface r of, we'll just use a trivial parameterization, r of xy. And so that would be x, y, and since I don't actually have a function, it's just whatever the function of xy is. Well, what I would have to do is I would have to find the partial here with respect to x. Well, the partial of my parameterized function here with respect to x is 1, 0, and then the derivative of a function of xy with respect to x is just f sub x. Alright, and then we're going to have to find the partial with respect to y, which is going to be 0, 1, and then again the partial of f of xy with respect to y is just f sub y. And then I need to do the cross product of those two things. I need to do rx cross ry. I don't like the way that rx looks like. R sub x cross r sub y. Well, if I cross these two things, we're going to cheat just a little bit here. If we put bars around here, I, j, k, like that, eliminating the I row and I column, you would get 0 minus fx. Eliminating the j row and column, you would get fy minus 0, but remember we have to change the sign. And then eliminating the k row and column, you're just going to get 1. And then, according to our formula up here, we need the magnitude of that. Rx cross ry's magnitude. Remember, magnitude is just the all of the pieces of the vector squared added up, and then you take the square root. So this is going to be the square root of, I'm actually going to go backwards here, 1 squared is 1, plus the square of the negative of fx squared is just the positive of fx squared, plus the square of negative fy is going to be fy squared. And so what we ultimately end up with is the double integral over d of the square root of 1 plus fx squared plus fy squared dA, which is exactly what we had at the top there for the surface area. So it does indeed work out. So that's how you'll find the surface area if you are given a parameterized function. You'll take the cross of the partials, and then you're going to insert those into the formula.